Okay, so today in lab, we are going to review some lab math, and then I'm going to teach you about these things called serial dilutions. It's just kind of like a preview of what's to happen next week. And I am realizing that I have the wrong slides up, so give me a second. We want this one. Okay, that's the one we want. Okay, so what are we doing today? Administrative stuff. So you'll have to give me a second. I need to pull up my rosters, but I am going to take attendance and not distribute the ad codes now, but at least tell the people who are going to get ad codes so that they can stay through today. And then everyone else, unfortunately, will not get an ad code. And then we will ask you to kindly see yourself out of the Zoom. After we get that taken care of, we'll do our review of Chem 155. So as a reminder, Chem 155 is a prerequisite for this course. And I've spoken with the professor of that course or the professors of that course and have looked over the syllabus. And some of the math that you supposedly learned in Chem 155 is something that we will be using throughout the semester. So when we go over the math today, it's not just for today, it's really for the whole entire semester. Okay, so, okay, after we do that, I might show you stuff about micropipettes. I need to see if I brought them home from work yesterday. So either way, I will talk to you about them and maybe or maybe not show them to you. Okay, but I'm thinking that most of you have used pipettes in animal or plant or some other science experience in your life. So I know that you've at least held them and I know you have looked at them. Okay, we will, like I said, talk about serial dilutions, and then at the end of lab, we will just go over stuff that's due next week, and then I will have the people that get an ad code stick around and I'll give you those ad codes. Okay, so a couple different questions in the chat. Was roll taken? Was roll taken? I didn't take it because that would have taken too much time, but I have a participants field, so by logging in, I can see if you were there or not. Okay. Okay, so I'm gonna give me 1 second so that I can pull up the attendance. Okay, so I'm gonna first call the people that are officially enrolled in the class. So let me know that you're here. So go ahead, everyone, you can unmute yourselves so we can get through this as fast as possible. And again, if you want me to call you something different or I mispronounce your name, please correct me. So I have Aaron Boyd.
So it says Ava works in the garden. She
Here.
Flowers a shower. So how
Okay. And then I have Ixaye.
What do you think they're talking about when they
Yeah, here.
Is that how you say it? Can you say it one more time for me?
It's Ixaye.
Ixaye. Ix like, okay, hold on.
Yeah, it's fine. Thank you.
I pulled them up over the fucking thing. The pillows.
Okay, Kylie Graff.
Here.
Armin Labashi.
Here.
Luis Navarro.
Here.
Helen.
Yeah, actually, that would be great.
Here.
Fena Rukema.
Here.
Rukema, maybe?
Rokema.
Rokema. Francisco Vega.
Here.
Alex Angel.
Here.
Clarissa Brock.
Here.
John Calzada Eloriaga.
Here.
Okay. Andrea Guerra.
Here.
Alana Haslam,
Here.
Mercedes Ledesma,
Here.
Eric Lopez,
Here.
Annika Sullivan,
Here.
Max Barris,
Here.
John Caples,
Here.
Lucy Gorek,
Here.
Morgan Hurd,
Here.
Jacqueline Lee.
Here. You got it right.
Okay, Lee. All right. Jenna Pham.
Here.
Okay. Grace Pori.
Here.
Awesome. Okay, so everyone is here. Thank you. And now I'm just going to call people on the wait list that are on my official wait list. All right. I have Carolina Mendeval,
Here.
Brooke Crockett,
Here.
Madeline Price.
Here.
Awesome. Okay. So I only have one spot available. So I am gonna just take the people on the wait list. So those 3 people that I just called, Carolina, Brooke, and Madeline, you can stay through class today and participate and get an ad code at the end. And unfortunately, I'm so sorry. I know that you really need this class. Everyone else, I know, I hear, I read you, I hear you. But we don't have any more positions available. I am very sorry. So if at this point you can log off from Zoom, that would be much appreciated. Okay. I just did a huge computer update and it's really hard to navigate this new system. Okay. Okay, so looks like we're ready to roll. Okay. Okay, so what I plan to do then is do one more Canvas tour, and after today, no more Canvas tours. I feel like I have shown you where everything lives in Canvas, where to find things, how to get there. So this is the last tour. It's specifically for lab stuff only. And so I will show you where the week 0 lab expectations document is, and that should have been something that you should have read before lab. And I'll just remind you that lab is 35% of the total grade. However, you need to consider lab like its own individual class. You have to pass the lab. And in order to pass the lab, you need a minimum of 245 points. Okay, so a minimum of 245 points. And the most that you can earn is 350 points. Every week, you need to get into the habit of expecting there to be reading and or videos that need to be completed. This is how you show up prepared. And every week, if maybe there's 1 or 2 weeks that this is not the case, but every week there is an assignment due the night before your lab. Okay. And just like you call the night before New Year's Day, you call it New Year's Eve. I call this Lab Eve. Okay, so assignments are due Lab Eve. So the night before by 11 p.m. on Canvas. Unless otherwise instructed, but for the most part, you're in the Thursday lab. Your lab assignments will be due Wednesday night at 11 p.m. Just like discussion, there are more assignments assigned than you actually need to complete so that you score the 150 points. So the assignments are 150 points total, more than you need to do. So for that reason, I do not take them late. I do not accept them late. Those assignments are different than lab reports and lit reviews. So it's 150 points for assignments, and then it's, I'll continue it down here. So it's 200 points for major activities, and these major activities is a lab report, okay, another lab report. These are just written. And then the third thing is a grant proposal, an abbreviated grant proposal, not like a real one that a scientist would submit. And that has a written and an oral component. It's kind of like your final in the lab. Okay, so there's where your entire 350 points come from. And I think I've mentioned it before, and I'll just mention it one more time. In 7 completed semesters of teaching this course, so that's, you know, almost about 700 students, only 2 people have failed the lab part. So the lab is very doable. It's a lot of work, and you will be working with groups, and you will have stuff always due. You're always working on something, but that actually keeps you accountable. When I didn't have all these weekly deadlines, I found that students really weren't deeply understanding the lab at all. They were just like doing the bare minimum to get through it, and they're leaving the class with no knowledge of lab, and that is not the point of this class. Okay, so most weeks you will attend lab and you will be put into breakout rooms, and that's why you need to come prepared, because I'm working under the assumption that when you show up today, you did the reading, you watched the videos. I don't reteach that. It's not like you watch it and then I reteach it to you the next day. Me teaching it to you was writing it for you to read and recording it for you, or finding valuable sources that break things down for you. And then in your group work, you come and you automatically start talking with your group mates about this, and then you share out to the class. So we do a lot of that. Lab is very much run like discussion, except discussions for lecture topics, lab is for lab topics. Okay, and then some weeks you will get unannounced POP assignments. So that's why it's so important to come to lab, not only because you have to come so that you can experience that group discussion. When Zoom assigns you to those groups, that also is going to be your group that you complete that assignment with. So if you don't come to lab, then you have to complete that assignment by yourself, because the group has already started doing work on things and it's not fair for you to join later. So you have to come to lab. And if you miss more than one lab, whether it's excused or not, you get dropped from the course. So this is a big chunk of time for this course, right? It's scheduled 4 hours and 40 minutes. So if you miss one, you're already missing a big chunk of time. If you miss 2, you're almost missing 10 hours worth of course material, and that's not acceptable. So please do come to lab. Please do show up on time. And these unannounced POP assignments, I don't call them quizzes, because quiz and exam to me means closed notes. It means stress for time. So anytime I give you a POP assignment, it's like, hey, work with whoever you want, but I'm gonna go ahead and let you leave. 45 minutes you have, open this assignment on Canvas, complete it. You have the World Wide Web available to you. You have your phone available to you. You can work in groups, I don't care. And usually the assignment is something that should take, like, I don't know, 15 to 20 minutes, and I'll give you 45 minutes to do it. So there should be no stress, no worry whatsoever. If you've done the reading and the videos, you should have a pretty good idea of the answers, and you just need to go back and look at your notes real quick. Okay, so that's really what lab consists of. Okay. So let's go ahead and I'm going to take us to Canvas so that I can just make sure that everyone knows where things are at. Okay. Okay, so here we go. We have our Canvas homepage. So week 0, that's where you could have or should have found the document with lab expectations. I'm going to go ahead and open that, because in case you did not read this, I just want to point out some of the things that I expect of students when they do show up for lab. So I really do expect you to read the readings and watch the videos. And like I said, I'm working on the assumption that you did that. So if you come and you're like, I have no clue what she's talking about, it's probably because you should have read the stuff and you didn't. So I form the lab discussions based on previous readings and videos. So I expect you to show up prepared. I expect you to show up on time. Okay, I also expect you to turn in the assignments when they're due. And I kindly, with respect, ask you not to ask if I'll take a late assignment because I don't take the late assignments. Okay, and when you do turn in these assignments, I ask that you do them with honesty and integrity. You can work with groups. I totally think that that's great, but everything you turn in, if I say, hey, every single person needs to turn in their own, that means you need to turn it in your own words. If it's a group assignment, then only one person from that entire group needs to turn it in, as long as everyone's names are at the top, and that's a group assignment. So there's a difference, and most of the things in lab will be group assignments. So most of the time you have a group of whatever, 3 or 4 people, one person will say like, okay, I'll turn it into Canvas for all of us. And that person's in charge of writing everyone's names at the top and getting it into Canvas on time. You don't need to have every single person in that group turn in the exact same copy. I actually ask you not to do that because it makes grading and organizing the grades extremely chaotic for me. Okay. So when you do get broken into breakout rooms, I do expect you to engage in the group discussion. So that does not mean you're just in the lab and you never join the breakout room. It doesn't mean you just sit there with your camera off. I do strongly encourage you, unless there's extenuating circumstances that do not allow you to do that, I expect that when you go to your breakout rooms that you have your camera on and you have your audio on and you're not using chat. So, you know, one of the things that people complain about with the online setting is the lack of community. Well, do the best that you can so that you can create your community. If you're constantly screen off using chat only, then this is not going to feel like a community. So you got to do your part to really feel like you're part of a group. Okay, so the other thing is, you know, breakout rooms, Zoom tells me if you've joined. So if your tactic is to just have your computer on in the background while you're cleaning the house or watching TV or doing whatever, it is apparent that you haven't joined your breakout room. It's apparent to me because Zoom tells me. So please join when you get sent to breakout rooms. And in general, not just in the breakout rooms, but in lab and in this course in general, I really do expect you to be a good teammate. And so what is a good teammate? A good teammate doesn't mean you have to do all the work all the time. Sometimes you have a natural leadership role. Take that leadership role. What that means, delegate responsibilities. That does not mean do everything yourself. And if you are the non-leadery type of teammate, that's okay too, but you need to honor the responsibilities that you commit to. If the leadery type of person is like, okay, you do this, you do this, you do this, let's all put it into the Google Doc by Friday, really do your part and do it well and put it into the Google Doc by Friday. And if for some reason things are really hectic in your life that week and you don't think that that's going to be a possibility, I think your teammates would rather you communicate that with them early rather than put in like a half-ass assignment into the Google Doc. So communication is extremely important, and communicating with respect and also listening with compassion. So you don't know what's happening in other people's lives. This whole pandemic is extremely unpredictable. You just don't know what's going on with people. So your first instinct should not be judgment. Your first instinct should be compassion. And I really do try to do that with students as well. And I expect you to do it with one another. Give people the benefit of the doubt. Let them talk to you. Let them explain themselves first without making judgments. And so if you are the person struggling, it's really up to you to communicate earlier rather than later, because that's what leaves like not so great of an impression. So people would rather hear that you can't do this by a certain day like you said you were, versus you don't do it and then you don't text back and then you don't communicate, and then 3 days later you say, oh, it's because I was sick. Communicate that earlier. Okay, so because your teammates might say like, okay, I'll step in for you, I'll help you do this, and then, you know, in our next assignment, maybe you can help me do that, and you can work out this kind of like agreement. And I think that's a way better way to go about this. Okay, the other thing is I expect students to be open-minded to imperfection, not just with technology and this, like yeah, I mean, yesterday was really tough in my office with technology. Wi-Fi was terrible, and that's no one's fault. And so I know that of you, and I know that of your places of living. So I expect you to have that same open-mindedness to imperfection with your teammates and with your lab mates, and be patient. And I really hope, I don't expect this, but I strongly encourage you to be open-minded to making mistakes, but what's most important is learning from those mistakes. Okay, so if things didn't go right in your first team that you worked with, learn from that in the next team that you're paired up with. Say like, all right, so here are the things that I hope that we can do in this team. And then finally, be gracious with yourself and with others. And number one thing is respect. Okay, respect yourself, respect your health, respect your teammates. And then I think that this will be a pretty good experience for you. Okay, so if we go back to our modules, every week, like we said, there's 3 different pages. The page that we're going to look at today is the lab page. So this has things that are important for week 1. And if you look at week 2, I've already put up, it's under construction, like I'm adding to it all the time, but the week 2 page for lab is already up. Okay, so if we click on week 1, the pages won't usually have stuff in the beginning. This is kind of just to introduce you to what pages are, what typically you can find on them, blah, blah, blah. Okay. But really the pages start with something that looks like this. These are the things to do before lab or by week 1 lab eve. You need to read the expectations, that document we were just on. You need to watch, take notes, and do the problems from this video. Okay, you need to submit. Nothing this week was due lab eve. Great. During lab, here I just outlined the things that we're going to do today or do in lab that week. So take roll and give out ad codes. So I've already taken roll. Discuss, we'll discuss lab expectations and format. I'm doing that right now. I'm telling you, you can definitely come with questions and answers about anything regarding lab. And then in the latter half of the lab, you're going to work in groups to solve problems, and then we're going to share them out. So if there's any files that I use in lab, I will post them here. Today, I'm using slides, but most times I just open up Notability to a blank document and I just start taking notes on there or collecting your information. So there's not going to be a lot of slides, like a formal lab slides every week, but this week there was. So those slides are there for you. They were there starting at the beginning of the week. And then I record these labs. I don't record the breakout rooms, but I try to record everything else. And so they are by day. So you are in the Thursday lab. There's no recording yet because it's being recorded now. But you can see that the Tuesday labs there. I don't know why Tuesday's little thumbnail decided to show up and Wednesdays were not, but there's that too. And you're more than welcome to look at those other videos if you want to see what you're in store for. Sure, that's up to you. And then at the end of lab, and which I will do today as well, we'll come back to this page and I'll tell you, all right, here's what we did, here's what to look forward to next week. And then I ask it if there's any questions and we log off for the day. And that's it. So just look for that. And if at any point in time, some of these links don't work for whatever reason, always know that you can go to the actual home of where these things live. So any kind of assignments are going to be in the assignments tab. Any kind of files, so slides, PDFs, any documents that I post are going to be under files, and they're going to be under lab. intro and lab math. So I've organized this as best I can to make it super clear. All of the pages for the entire semester are in the tab called pages, and you can see them all here, but this to me is really overwhelming, so I never use this page. But if for some reason you need to, like you're like, well, is that one page? I don't want to look through each of the modules. I want to find them this way. Go for it. Find them that way. Okay, so I think that that covers it. So are there any questions about the lab setup for now on Canvas? Okay, sweet. Okay. All right. Okay, so at this point, we don't need to go over the Q&A, how do you use it? You guys are doing an awesome job doing that in lecture and discussion, so we're gonna keep on moving. Okay, so we're gonna move right into the lab calculations. And so that video that you were to have watched has the examples of all the different types of math problems that we're gonna do today in class. So what you're gonna do, and we're gonna do two different types of approaches. The first approach is that for the first set of questions, I'm just gonna put you into your breakout rooms right away, and you're gonna work on these problems and figure them out together. And then for the next set of questions, I'm gonna have you work by yourself first, and then I'm gonna send you to the breakout room and discuss that with each other. So hopefully by the end of this first breakout session, you feel a little comfortable remembering how to solve these typical problems. And it's not like word problems, this is not math class. The idea here is, would you be able to physically walk into a lab and actually make solutions at the lab bench? And I know we can't physically do it, but you can literally write instructions on how to do that. And if you can literally write the instructions on how to do that, then I am pretty confident in you that you would be physically able to do it. Okay, week 1, new semester, voice out the window. Okay, sorry. Okay, you'd think my voice box would be used to this. It's not. Week 1, it's terrible. Okay, 32 millimolar. I'm going to have you convert that to kilomolar. And I'm going to have you convert that to micromolar. Okay, so the symbols for the units were covered in the video, and you can work with your team to do this. And so the point here is, so when you're in your group, think about these things. You want to show your work, and imagine that you're showing your work as if you were going to turn it into an exam for credit. So it needs to be organized, and it needs to be clear what you're showing. So when you're in your group, maybe whoever has, if anyone does have a tablet that they can write on, great. If you can't, I had people write nice and big on a white piece of paper and then show it to us. That works as well. The typing or the Zoom whiteboard to me is awful, and it's slow, and it's just, but if that's what you choose, think about it like this. What would you turn in for full credit? How would you teach someone else this? So if you think the Zoom whiteboard is a good teaching tool, use it. If you think writing, use it. If you think tablet, use it. But you have to show something. And then when you are showing the class, you are going to walk us through this. So if I was showing you this, I wouldn't just show you and just talk it out. I'd have my finger, and that's kind of hard, but I'd have my finger and say, like, first he looked at these things called animalcules. Okay, there's that. And then we divided by 100 to get microscope. Okay, awesome. So you're gonna walk us through, like you're teaching us these things. And if someone is presenting and verbally, but someone else is sharing the screen, that other screen sharer should try to move the cursor so the rest of us know where to look while you're talking. Okay, so that is the first of the 3 questions that you're going to answer. The next one is a little more complex. So conversions are easy, just to make sure that you know which conversions you should have memorized. So example, when you have a liquid that's super concentrated with an actual concentration value and your protocol in the lab asks you to use that reagent at a less concentrated value and a certain volume. So what equation do you need to use? If you're using an equation, you need to define the variables. So you should have that somewhere in your showing your work section. And then here's the important part here is that I didn't just say show your work, I said explain. So explain to me if you had to write a 2-step instruction, how would you make this? And I showed a very clear example of how to do that in the video that was to be watched last night. Okay, and I'm gonna give you a clue now. Always make sure that your units of concentration match. If they don't, step 1 always has to be convert. Units of concentration and volume do not have to match one another. Concentration and concentration do. Okay, so write this down because when you go to your breakout rooms, the PowerPoint slide disappears. So explain how to make 50-liter solution of 25 grams per mole NaCl. And I tell you your lab stock is a liquid solution of NaCl and it is at 0.1 kilograms per milliliter. The next one is another example the same way. So you have a very concentrated solution. You need to make a less concentrated solution. Explain how to make 25 mils of 400 micromolar NaCl. The lab stock is at 8 millimolar. Not only show your work, but write 1 to 3 steps of how to do this in a lab, physically how to do this in a lab. You want to include things like, do you need a graduated cylinder? Do you need a flask? Do you need a stir bar? Do you need a scale? Do you need a pipette? What are the things that you need to do? Like if you had to instruct someone like, okay, so you're gonna go to the bench and blah, 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 you're gonna explain to them what to do. Okay, okay, so any questions on what you are going to do in your groups? Okay, so what we're gonna do here then is I will break you into rooms of approximately 3 to 4 people. Cool. And when you go there, don't forget, write your breakout room number down. And then the team manager for the day is the person whose first name starts with the letter that is closest to the letter B as in banana. Okay. You will be the team manager. That means you have to manage a couple things. You have to manage, all right, who's gonna be the one that is going to take the notes that we're gonna show? Who's gonna be the screen sharer? The team manager, you are the verbal presenter. And the team manager, you're gonna also make sure that you keep your team up to speed with time. So you will have 20 minutes to do these 3 problems. And in those 20 minutes, I'd say maybe allow yourself 5 minutes for intros and the conversions. And then maybe another 8 minutes for the second problem. And then move on to the third one. So keep track of time. I will give you a 5-minute shout out, what is called broadcast to all. So with 5 minutes to go, I'll say 5 minutes and make sure you're ready to present. And then when we present, I'm gonna call breakout rooms randomly. So if you're breakout room 1, that doesn't mean you're gonna present first. You never know. So that's why it's important to get to all 3 of these questions. And just like in discussion, if you share your screen, I'm going to be asking questions. And I'm going to be asking questions to you, to the rest of the class. You don't have to have it right. This is the part where who cares if it's right or wrong. I'm going to ask questions like, why did you do it that way? It's not because it's wrong, but I just want to know that I want to know your rationale because I think other people will benefit from that rationale. And of course, I will step in if things are going the wrong direction. And still, even if it's wrong, that's okay. Okay. So this is our self-building confidence session too. It's okay if things are wrong. Okay, I think that's it. So I'll go ahead and break you out. It's 10:36 now, so we'll be back in the class at 10:56, and this 20 minutes is more than enough time. Make sure nice big writing if you're going to actually write on a piece of paper, because it's really hard to see, like it's hard to see small writing. Nice big writing, and good luck. I may not be in this area, but my house is tiny, so if you need help, just shout to me, okay?
Okay, so for our conversions, so for the first one, when you're going from millimolar to kilomolar, you want to move the decimal place back over this way 6 times, because it's a multiple or of 10, or is that the right term?
It's
So you want to
it's a factor of 1,000.
factor of 1,000. Thank you.
Yeah.
And so we did that twice
Mhm.
in order to get to kilomolars, and then from millimolars to micromolars, it was just a factor of 1,000.
Mhm.
Okay, just one factor of 1,000, and then
Oh, that's
for
it.
the
You only have to do.
oh, wonderful.
So thank you. Yeah. So you leave that up for one more second. So I really like how it is obvious how many times this group moved their decimal place over. So those little curves, that shows me the number of decimal places that they're moving over. And then they did not put it in scientific notation, even though scientific notation would have been correct. I want to see that you know the actual number. Because if I said, okay, what's 3 times 10 to the 8th, you're going to say like 3. You would be putting all the zeros anyways to tell me it was 30 million. See, even I don't know off the top of my head. Like I have to have the zeros there to know. And the only other thing, if you are writing stuff, you won't be doing it often because things are online and all the answers will be typed. But you want to make sure if you are submitting things that are handwritten and you're showing your work, just clearly make the micro, make it a lowercase u as opposed to the Greek symbol mu. So mu is that like curly M, but right now it's hard for me to see, are they showing a lowercase m or a lowercase u? Just be really unambiguous, and then that's the only comment I have. Okay, and that's for everybody. Okay, so go ahead and stop sharing your screen. I'm gonna go outside and scold my dog. But the next group that I'd like to share their calculation for the next problem is breakout room number 4. Paloma, enough, get in here.
Which one would you like us to share?
The next one.
Oh, the next one.
Mhm.
Okay, we had a little bit of like a debate on how to work this one out, but what I remember from the video that you were explaining was that you take this, the NaCl, and then you pour it into another graduated cylinder. And I remember you said try this one on your own. I tried it, but I was having a rough time, so I'm gonna have to ask for help on solving this one.
Okay, well, let's start with what we know. So no one in your group was able to come up with a solution here?
I believe Lucy came up with something, but she didn't really know how to explain it.
I don't know how to explain how I got to it. I kind of did the math in my head, and I know that we converted 0.1 kilograms to grams.
Okay, let's start with there. Let's start with, so I see that you wrote this magical equation on your tablet. C1 equals C1 equals C1V1 equals C2V2. Why did you write that on there?
Because that's the equation you provided on the video.
Okay, but there's a lot of equations that you could potentially use for lab math. So it's really important that students understand which equation they're using and why. So what, if we're just looking at that equation, what is C1 and what is V1?
Concentration and volume.
Great. Okay, now what's 1 versus 2? Why does some of the C's have a 1 and why do some of the C's have a 2?
Because you have your starting concentration. Sorry, you can answer.
Yeah.
Chris.
No, you can go, Lucy.
You have your starting concentration of NaCl, and then you have the concentration you want to end with. So concentration 1 is your starting concentration, and concentration 2 is your final concentration.
Okay, so you already, your team knows way more than you're giving yourself credit for. So you already know what those variables mean. And now I'm gonna ask you, okay, so you know that C1 is the concentration that you have, right? You just told me that. From the information that I gave you, do you have C1 from that problem?
Yeah.
What is it?
100 grams per milliliter, or 0.1 kilograms per milliliter.
Okay, so first step, C1 equals, yes. Where's the units? Okay. Okay, so I'm gonna now ask you, how did you go from 0.1 kilograms per mil to 100 grams per mil?
I converted kilograms to, or I just, honestly, I used Google.
I have it figured out. I just need a little bit more time because I was working on the other one. And I know we were going to be doing this one, but I don't know. Is it mirrored? Okay, never mind. I'll just try and explain it because I don't have it written down, but because I did it on paper, I don't have like a tablet for it. But so we have to get like all the units on the same page. So we would convert 50 liters to milliliters, which would be 50,000 milliliters. And then we multiply that by our solution amount, which would be the 25 of NaCl. So then 50 milliliters times 25 grams per milliliter would give us, what was that? 1,250,000 grams per liter or per milliliter.
Okay,
And then we set that.
Hold on. So you did, converting is fine, the volume, but you don't actually need to convert the volume, right? So that's one of the things that I had said is that concentration, the concentration units need to be the same. So we just did that. So I think, who was sharing their screen? Carolina?
Yes.
Okay, so Carolina wrote C1 equals 100 grams per mil. And the reason why she did that is because she saw that the concentration she wants to make was in grams per mil, not kilograms per mil. So the concentration she has and the concentration she wants, now those units match one another.
Yeah, that's what I was saying.
But you don't have to do that for the volume.
Like for the 50 liters?
Correct. You can just leave it as 50 liters.
Okay.
Okay, so C1 is, who's talking, by the way?
John.
John, okay. So C1, we've already established what that is. So let's go ahead and still define all of the other variables. Okay, so C1 we know. Do we know V1? Yes or no?
No, that's what we're solving for.
Okay, so Carolina, please put V1 equals question mark.
Okay.
Sure, that's fine. That's fine. How you're doing it is fine. Okay, great. Now we go to the other side of the equation. So do we know our C2?
Yes.
Yes, it's
What is
50
it?
liters.
25,
C2.
25 grams
that
per milliliter.
Yep. Okay. So maybe above that 25, maybe you can write C2 so we know what that is.
Yeah, I'll just move it over here.
Cool. Okay. Great. Awesome. Do we know V1, yes or no?
No.
V2, sorry.
V2.
Yeah,
Okay, what is it?
50 liters.
50 liters. So go ahead and write V2 equals 50 liters. And I know that the intuition to want to change that also to milliliters is there, but I'm going to show you why. So go ahead and fill out the rest of your equation and then actually write, solve for V. Don't skip any steps, do the algebra.
The 1,250 divided by 100.
Units for every single thing. Yep. Yep. Cool. So pause. Now you can see how the grams per mil, it's on the top and it's on the bottom. So those two things cancel out. So just put a big X through those units. Perfect. And the only unit left over is liter. So that's why you didn't need to convert to anything, because trying to measure out 50 million milliliters, that's crazy. There are definitely flasks and measuring devices in the lab that will allow you to measure in liters. Okay, so now I'm gonna ask, so now I'm gonna ask 12.5 liters of what?
Water.
NaCl solution.
So there is a little bit of conflict in this team, so it's not of water, it's of NaCl. What NaCl solution?
Wait.
The original NaCl solution.
Which would be 0.1 kilograms per
Yeah.
mil. Okay, so the first thing that you would need to do is get yourself a big empty Erlenmeyer flask or a big giant beaker, some empty thing, because it has to hold 50 liters, a carboy, whatever. And the first thing that you're gonna add is 12.5 liters of 0.1 kilogram per mil NaCl. So like your little diagram is showing you, you're going to take your stock and you're going to take 12.5 liters of it and you're going to put it in this empty beaker that you're going to label 25 grams per mil.
Right, and then you fill it to the 50 liter mark with water.
Yeah, and so if you have 12.5 liters of NaCl, how much water do you need?
37.5 liters.
Correct.
Yeah.
Yes.
Okay.
So the instructions are then to use or pour 12.5 liters of 0.1 kilogram per mil NaCl stock into an empty beaker. Then add 37.5 liters of deionized water to that same beaker and mix well. Those are your 3 steps. Add the solute, add the solvent, mix it up. Voila, you're done.
Thank you.
Yeah.
All right, thank you so much.
You're welcome. So hopefully that shows everyone, it doesn't matter if you're kind of confused along the way. We work as a team together and we figure it out. And that was perfect. So thank you to group whoever. What team were you for?
4.
Okay, thanks. Okay, so let's go ahead and move on to the last problem. And it's a very similar problem. So now group 6 is going to have no problem explaining it. And if you do still have problems explaining it, we'll just help out like we did last time. So group 6, last problem.
Hi, I think that's us. I don't have a tablet, but I wrote it down as large as I could.
Who's us? Who is speaking so I can try to pin you and make
Fenna.
you? Fenna. Okay, hold on. Let's see. There you are. I'm going to add a pin to you and then I'm going to unpin myself. So now everyone, if you have it on speaker view, Fenna should be nice and large on your computer screen. And when she shows us whatever she's showing us, that will also be nice and large.
All right, so we have our work here. And I can't really see myself, so I hope this is large enough.
Mhm.
But basically I wrote out the problem, and then the first step that we had to do is convert our stock solution to the same units that we want our final solution to be in, or the final concentration of our solution to be in. So I converted the 8 millimolars over here, or 8 millimolar to micromolar, using the conversion factor right here, because that's the way I learned it, and that's the way my group learned it. But we basically multiplied it by 1,000 to move the decimal places, or the decimal place 3 places to the left, or to the right if you're looking at it. And so we found that our lab stock is going to be 8,000 millimolar lab stock. So then we assigned our concentration values using that same equation that we used last time. So our C1, or our initial concentration of what we have, is going to be 8,000 millimolar. Our V1, our final volume, or our volume of that stock that we want to have, is unknown. Our C2 is going to be our concentration of the solution that we want to have. So our final concentration that we want, which is going to be 400 millimolar. And then our V2 is the volume of solution that we want to end up with, which was 25 milliliters. Or this is micromole, sorry. So we just plugged everything into the equation right here. We had our C1 times V1 equals C2 times V2. And we solved by dividing both sides by the 8,000. And we ended up with our V1 equaling 25 millimolar, or milliliter, excuse me, 1.25 milliliter.
Okay.
And so I explained it as, and I can just say it out loud too, to add 1.25 milliliters of our 8 millimolar NaCl lab stock to a graduated cylinder, then to another graduated cylinder add 23.75 milliliters of the distilled water to another graduated cylinder, and then combine them in a beaker to form the 25 milliliters of 400 micromolar NaCl solution.
Okay, awesome. Yeah, that was great. Clap, clap, clap. That was awesome. Really straightforward. The writing on the piece of paper was very clear. The variables were defined. Ixay is saying to mix. Yes, mix
it together.
Yeah, and that's pretty much it. Any questions, comments, anything that I need to clarify or go over for the class? Okay, thank you, groups. So that was great. So let's go ahead and move on to the last couple of questions. So what I was just doing was following along with what Fenna was saying, and I was writing in my own notes. I was pretending I was a student, and essentially, you can use that later if you didn't get the answer right, or it was solved by this group a different way than you did. You can, you have now 2 ways to solve it. Okay. So the last 2 problems that we are going to work on, this time you're going to work by yourself for about 7 minutes, and then you're going to work with your group for about 5 minutes. So 7 minutes should be enough time for you to do both of these problems. And so the one thing I want to make sure that everyone understands when you go to a group, I know the tendency is there's 3 problems, there's 3 of us, let's each just take 1. That's an okay approach, but you have to leave yourself time to talk to the rest of your team. Like if you were in charge of question number 1, you as a group need to leave yourself time so that you can explain number 1 to your other teammates, because otherwise there's no point in doing group work, right? The point of group work is that all 3 or 4 of you know how to solve all 3 of the problems. So do make sure that you keep that in mind when you're in your groups. Otherwise, it's just you working independently in your group. There's no point in group work. Okay, so for this next one, you are going to be working independently in the beginning, and then you're going to share out your answers with other people. So in this example, this is when you come to the lab and your protocol asks you to make a certain stock solution, or so you know how up here we had a lab stock of 8 millimolar Somebody had to make that, and it came from solid plus liquid. At some point in time, that solution needed to have been made from NaCl salt and water and dissolved. So that's what this is, a solid plus a liquid. Now in chemistry, I think oftentimes the solutions are presented in molarity. In the lab, we like to use percent solution. In the molecular bio lab, we like to use percent solutions. Don't ask me why, but it's really common that we use percentages. Also X, like, oh, this is a 10X solution. That just means it's 10 times as concentrated as you normally need it. Why we do it that way, I don't know. Okay, so to make these percent solutions in molecular biology, you can always assume, unless otherwise instructed, you can always assume that the buffer or we should call it diluent or solvent, the thing that you're going to dissolve the solid in, you can assume that it has the same density as water. So this liquid, people like to call it solvent. That's usually when they're taking a solid and dissolving it. And you can remember that you solve in solvent. Other people call it diluent. That's typically used when you're taking a more concentrated liquid and diluting it. That's why we call it diluent, okay? And you can assume the density of water unless otherwise instructed. So you're going to work on your own to explain how to make 35 milliliters of a 0.8 agarose solution. So here is some information for you. This is the total desired volume that you want. Total volume needed. Here is your solvent. Here is your solute or solid. Okay, and then here is the desired concentration. So I know sometimes percentage gets a little into people's head and messes with them. So just assume this is the equivalent of like a capital M. It's just a unit of concentration, okay? Maybe that helps keep track of things a little bit better. And so with the density of water, what you want to remember is if you somehow, not somehow, this is exactly what would happen. If you took, here's your scale, okay? If you weighed 100 milliliters of water, so here's your flask, you tear the scale and you pour 100 milliliters of water in there. What is the scale going to read? Please put it into the chat. Because that's what density means. I'm going to let a couple more people go. Okay, so we have some guesses here. Right now there's only 2 and they're very different. Okay, cool. So if you took 100 milliliters of water and threw it on a scale in a flask or a container, that scale would read 100 grams. Okay, so the density of water is 1 gram per mil. And we memorize that, but we forget sometimes what that actually means. It means that every milliliter of water actually weighs 1 gram. Okay, so now, so that's our knowledge of the density of water, that 100 mils would weigh 100 grams. 5 mils would weigh 5 grams. 1 mil would weigh 1 gram. Okay, that's what the density of water means. Now, I'm going to draw your memory to what you know of what percentages mean. So if I said, hey, I want you to write 5% as a fraction, how would you stick it into your calculator? Pretend the chat is a calculator. What would you write in your calculator? Yep, that's exactly what you would write in your calculator. You would write 5/100 if I was asking you to put it as a decimal or a fraction and then a decimal. So if you wrote this instead of a diagonal decimal, if you wrote it as a numerator and denominator, you would also argue that 5% is equal to 5/100, right? Yes. Okay, so that is our knowledge of what percent means. This is our knowledge of density of water. Okay, one more knowledge. Now we need our knowledge of concentration. What is concentration defined as? Only one person knows. I don't buy that. Okay, I'll wait. If we technically have till 2:40. So what is concentration defined as? Okay, it seems right. It is right. This is a chem concept, okay? Yes, concentration is mass over volume. So if you take all three of these pieces of information and you use them to create percent concentrations, essentially what you need to do is if you needed to make a 5, let me change the color here. If you needed to make a 5% solution of something, you know that it's going to be 5/100. But if you're dealing with actual concentrations, you also know that mass has to go over volume. And so mass will go over volume. In this case, mass, because we said, hey, every time you're using a scale, you're using grams. And every time you're using volume, you're using milliliters. So a 5% solution is equal to, if you had to make 100 milliliters of it, you would weigh 5 grams and of the solid, and you would add it to 100 milliliters of the liquid, which is the solvent. So that's how you would make a 5% solution of whatever at 100 mils. But we don't always want to make 100 milliliters. Sometimes we have to make less, or sometimes we have to make more. And so when you have to make more, that's when you just set up a very straightforward ratio. So if we have 5 grams per 100 milliliters, this is our kind of like our known, right? This is our, it's actually our desired, because it is 5%. So we'll just say this is a 5% solution, but we don't want to make 100 milliliters. We want to make some other desired volume. So you have a desired volume that you know that you need to make, and you're trying to figure out how much do you need to weigh of it. Okay, but this would also be 5%. It's kind of almost like a conversion, but you're just using a different volume. So this is how you would solve any percent solution when the buffer or the solvent is the same density as water. Okay, so keep that in mind when you solve this problem. And then the next one is you have a liquid solution, but the protocol is asking you to add a specific mass, okay? So let's say you had a bottle, big fat bottle of liquid sucrose, so sugar water. And the sugar water, so this is sucrose solution. Okay. The concentration of it is 550 micrograms per milliliter. So we're going to draw back to really think about what this means. What this means is every time you set your pipette to 1 milliliter, if you had a magic scale that could weigh just the sucrose molecules in that pipette tip. So here's your pipette tip. It's attached to a pipette. Uh-oh, this is gonna be hard for me to draw. Okay, so here's your sucrose liquid. And if you had magic goggles, you would know that that means that there's sucrose molecules floating around the solvent, right? So let's just draw some sucrose molecules in there. And this was set to 1 ml, so this is 1 milliliter of liquid. If you were able to just pick out those molecules and put those molecules on a scale, so here's your little weigh boat, and you put just the molecules, somehow you were able to take just the molecules, no liquid, and weigh it on a scale, that scale would read 550 micrograms. That's what 550 micrograms per mil means. It means every time you take 1 ml of solution, you're actually taking 550 micrograms of mass, right? Because concentration is mass over volume. So if you took 2 mils, you would take 2 times 550. If you took 10 mils, you would take 10 times 550, and you can work the other way too. Okay, so what it means is that for every 1 milliliter of liquid, you are actually taking with your pipette or measuring out 550 micrograms. Sometimes you don't want exactly 550 micrograms. Sometimes you want a different amount so you have your desired mass. Okay, that's like your protocol says, I want 22.5 milligrams. And so what you have to figure out is the amount that you have to set your pipette to or pour into a graduated cylinder so that when you do, you're actually taking your desired mass. Okay? Anytime you have a ratio set up like this, you do crisscross multiplication. Okay. So with that kind of recap, so this is an example, what I just did for you right now is something I won't do for you in the future because this was explained in the video, right? So I re-explained it, something I don't necessarily do every lab. Please don't get in the habit of it, but I want everyone to feel comfortable with this. Maybe you didn't really think I was gonna expect you to watch the video, but now you know I do from this point forward. Okay, so one more time. Here is the first problem that you're going to work on by yourself. How to make 35 mils of a 0.8% agarose solution using powder and TAE buffer. Next one is if you have a sucrose solution that is at a concentration of 550 micrograms per mil, how much liquid do you need so that you're actually adding 22.5 milligrams of sucrose mass? Okay. So always keep your units there so you'll never get confused and always have the right units in your answer. Any questions before I let you go do this on your own? Go ahead, Andrea.
So we're answering the second problem as well that's up on the screen right now?
Yep, these two. Yep. Okay, 7 minutes, it's 11:32. Let's just round up to 8. I'll bring you back at 11:40. At 11:40, I'm just gonna send you to your breakout room to start talking about it, So we won't record this as everyone's working. So we're talking about how scales are used in the lab and how all of these problems that we're doing today really are to help a student understand how they would literally, physically do this in a lab. So let's see, who is this that is talking to me right now?
Jenna.
Jenna?
Mm-hmm.
Okay, thank you. So she was explaining how she is going to make a 0.8% solution of agarose in TAE. So I was taking notes on what she said, and now I'm going to just share my notes according to what she said. Okay, come on. Okay, so she said the first thing she did was she put 0.8 grams over 100 mils, and that is because she wants to make a 0.8% solution. And that goes back to what we said up here, that whole entire explanation that I had, is that if any percent that you want to make, you're always going to put that value on the numerator, and that's the amount of grams you would want, over 100 milliliters. And so this value comes from the density of water. Well, actually this whole entire value. So if you wanted to make a 5% solution, you'd put 5 over 100. If you wanted to make a 10% solution, you'd put 10 over 100. If you want to make a 0.8% solution, you put 0.8 over 100. And so that's what she did. She said that she put 0.8 grams over 100 milliliters. And then, as I explained before you went out to your groups, you set up a ratio. So what was the ratio that I said we needed to set up? We set up whatever desired percent. So now let's just write it here. We desire 0.8 grams over 100 because we desire 0.8%. But the desired volume is not 100. It is 35 milliliters. We still solve for grams, okay? And so we take that, let's see, I think I can even take it like this. Copy it to a nice clean page. Okay, so there it is. Let's rewrite it so it's nice and neat. So we are gonna solve for the number of grams, because that's what we're trying to figure out. How much of this do we stick on a scale? Okay, and we know that we're going to make a total of 35 milliliters, and we're not mixing it in water, we're mixing it in TAE buffer. Okay, so chicken scratch to solve it quickly on your own, no problem, but when some of your points come from showing your work, it needs to be really nice and clear. So really quick recap of algebra. Crisscross multiplication, all that means is when you have two fractions set up, then all you need to do is you take the diagonal numbers that you have actual values for. So if you look at these two ratios, these are the numbers that are diagonal of one another and you have actual numbers. You multiply those together. That's crisscross, that's the multiplication part. So you have 0.8 grams times 35 milliliters. Then you divide by the remaining number you have. This is not a number, so you don't divide by a question mark. This is a number, so you divide by that number. So you divide by the remaining number you have. Okay? And so what you can see here is that your units cancel out. Some of them do. So you have milliliters on the top, milliliters on the bottom. So those cancel out. And so what you stick into your calculator is 0.8 grams times 35. Then divide that by 100. And I think that comes out to 0.28. The only units left over is grams. So I would say, like, if you're weighing something out, just get your answer. And if the answer seems like, ooh, then I should convert, go ahead and convert. But I think what Jenna had gotten before was she got something like 2.8 times 10 to the negative 4th kilograms. Is that what you got? So if this was the directions that you gave, if I gave those to you in a protocol, I'm like, okay, go do it. You're gonna say like, oh, what scale does that? I don't know. So you would naturally convert that value to grams anyway. So if this is the answer you got, you can clearly see you don't need to convert from that point. So as she said, when you're explaining it, you would say weigh. So there's your answer, 0.28 grams of. So what are we weighing 0.28 grams of?
TAE buffer.
So buffer is a liquid. Can you weigh grams of liquid?
The agarose.
Yep. Yep. So 2.8 grams of the solid, because solids can be weighed on a scale. And then you add to a flask, a beaker, or whatever with 35 milliliters of, what are we adding 35 milliliters of?
0.8% agarose solution.
That's what you're making. That's the final that you're making.
The TAE butter.
The TAE buffer. Yep. Okay. So if you had to draw it out, what it would look like is, here's your Erlenmeyer flask that's empty. You are going to weigh out, here's your agarose powder that weighs 0.28 grams. That's your solid. You put that into a flask. Then you use a graduated cylinder. And you fill it to 35 milliliters of TAE buffer. So that's probably going to come from a giant carboy with a little spigot that you pour. So it's a humongous, maybe has like liters and liters and liters of TAE. So you pour that into your graduated cylinder, and then you pour that into that same flask, and then you mix. What that gives you is a 0.8% agarose solution in TAE. So it's really important to know not just the correct numbers, but weigh 0.28 grams of what? Add 35 mils of what? When you add those two things together, what does it actually make? Okay. So hopefully that clarifies things for you just a bit. Any questions on this? Okay. So thank you to Jenna and Alana for getting us going on this. So now let's go to the next problem. So let's go with breakout room number 3. Please show your work and explain how you would solve this problem.
I think Alana.
Oh, wait, did I already ask breakout room 3? Okay, sorry, let's go.
Sorry, I was writing everything down. I'm so sorry.
No, it's fine. I picked the wrong room. Let's go with room number 1.
Hello, that was my group.
Okay.
So do I start off with the answer or do I do the step-by-step?
But you're teaching the class. So if you needed to be taught this, what would make most sense to you?
Okay, so I took sorry. So first I converted the U.
Yeah, you want to show us too.
Okay, my bad. It's a little messy, but that's what I have. So I converted the 550 UG to grams, I believe. So I got 550,000. And I put that on top of the 1 milliliter.
Okay, so you moved the decimal place over the wrong direction.
Oh, I did?
Mm-hmm.
Okay, well, should it have been to the left?
Yeah, because micrograms to milligrams, you want to move the decimal place
Yeah.
over so the answer is smaller.
Yeah, I don't know why I did that. Okay, so I guess I can redo that. So 550
Mhm.
grams over the milliliter is equal to this desired mass, and that was 22.5. So then I put that there, and the X stands for the milliliter value that we don't have yet. So I just crisscross multiplied, and I got a wrong answer, but I can redo it again since I didn't do it right the first time.
Okay, so we'll give you a second to do that, and I'm just taking notes on what you said.
Yes, and I got 40.9 milliliters.
40.9 milliliters.
No,
I think 40.9 is right. I need to get out my calculator in 1 second though.
yeah, I got 40.9, but I'm not sure about that.
Okay. So let's see.
Sorry, my work was kind of messy.
That's okay. So lesson for everybody, make sure that your work is not messy so that you can go back later and use it as a study guide. So why don't I share what I took notes on and according to what you said. So let's see. Okay. So Andrea said the first thing she did was converted. So granted, she converted the wrong way, but it doesn't matter. Her approach was correct. She knew she needed to convert because she saw that the concentration was in micrograms, but the mass that she needed was in milligrams. So she needed to convert. So you would take 550 micrograms, and you know that if you needed to display it in terms of milligrams, you would divide by 1,000. So dividing by 1,000 gives you 0.55 milligrams per milliliter. Hopefully everyone agrees with that. So essentially what that means is every time you set this pipette to 1 milliliter, you're actually taking 0.55 milligrams. Okay, so then she used this ratio that I kind of started setting up for you, and she just plugged in the stuff that she knew. So instead of writing it in 550 micrograms, she did it in milligrams. So it's 0.550 milligrams. And that is anytime you set your pipette to 1 mil. And then she used the other side of the ratio to set up her desired mass, which as we know is 22.5 milligrams. And then this is the value that you're solving for. And so then she said that she did crisscross multiplication. So the second part is to solve for X mils. So to do that, it's 22.5 milligrams times 1 milliliter divided by 0.55 milligrams. Let me do that real quick. Okay, so yeah. Okay, great. So you were right. Thank you. So it was 40.9 milliliters. So now I'm going to ask you the questions that I asked everyone else. 40.9 milliliters of what?
That would be 40.9 milliliters of, oh, I had this, but so it'd be of the, I don't know. So it'd be of the solution in the jar.
Yeah, so what is the solution in the jar according to my little diagram here on the picture?
What is the solution? It's, I don't know. Like anyone
remember what I said the solution was in this example?
Sucrose?
Yeah, sucrose. Okay. So the protocol was asking for 22.5 milligrams of sucrose. You don't have it anymore solid, but you do have a sucrose solution. So you would say, the correct answer would say, take 40.9 milliliters of 550 microgram per mil sucrose solution. So that's pretty much saying that you're going to pour out from this jug into some sort of graduated cylinder. Graduated cylinders don't go to the 0.9, but your answer is still 0.9. And you would say, use a graduated cylinder to pour 40.9 milliliters. If you were actually doing it in the lab, if it was me, I would just round up to 41 and that would be fine. But you want to measure out to 40.9 milliliters. And then you pour that into your whatever experimental solution you're making. And that's it. So that's how you would obtain 22.5 milligrams of sucrose if you don't have actual solid in the lab. Okay. So yes, Carolina, you can round to 41 when you're making it in the lab, but your answer should still say 40.9. Okay, great. So those are the typical math approaches that are used very, very often in molecular, micro, cell, any kind of biomedical research lab uses this type of math all the time. So what I want to present quickly, and so this is now, we are getting into a preview of what is going to happen next week. So for this stuff here, I don't go into exhaustive detail because I'm going to kind of preview it now. You're going to read a little something about it. The worksheet that's due next week has a couple questions about it. So I just want to gloss over this. The typical pipettes, so I did bring them home. The typical pipettes that you see in a lab, I think everyone has seen one of these before. They differ by the volume that they can, the word is aliquot. Aliquot just means measuring liquids. And you can see that this one that I'm holding right here has a very long, shaft that is going to use the largest tips. And then you have kind of like Goldilocks and the Three Bears. This one in the middle will aliquot medium-sized volumes, and then this tiny one here will aliquot tiny volumes. And so these are the three common sizes, but you can actually, there's bigger ones and there's even smaller ones in this. So I'm just gonna kind of go over the common ones, starting with the one that aliquots the largest volume. They're called P1000. And if I show this too close to the camera, it gets blurry, but I just do want to point out that if you looked at the top of the pipette, you can't really see it. Maybe you can. You definitely can see that there's writing or typing on there. And that typing, what it does say is P1000. And some of them even tell you the pipette volume range. So it's like, don't go below this, don't go above this, for two reasons. One, it ruins the spring inside of the pipette, and that ruins the pipette, and that wastes $500. And two, this pipette is not accurate if you go above or below the range. So P1000s, this one specifically, can aliquot as little as 200 microliters and as most as 1,000 microliters, which is the same as 1 milliliter. Okay. We always talk about volumes with pipettes. We talk about them in microliters, which is why we call these micro pipettes. Even though this large one can aliquot 1 milliliter, that is 1,000 microliters. Okay, some P1000s can actually aliquot as low as 100, but again, it's usually written on the top here. And so each of the pipettes have a little window. You can see it. Numbers don't really matter at this moment, but maybe if I zoom in closer, you can see this little number right here, 3 numbers. You always read it top to bottom. And so you can even see it here. For a P1000, the top number is always red. Okay, and that top number can either be 0 or 1. It can never be more than that. You should not even twist this black thing. This is how you adjust the numbers here. So if I turn this, you can see that the numbers are changing. You should never twist it beyond 1. That's ruining the spring inside the pipette. The other numbers are black. So let's see, it's set right now to 2, 9. So if I was gonna give you this right here on some kind of worksheet or exam or whatever, and I said, hey, the only pieces of information I give you is that this is a P1000, and this is, well, I say that there's a 0. And this is what it is set to. Tell me how many microliters this is going to actually measure out. And so you always read from top to bottom. So if you read this from top to bottom, you would say that this was 29. Would you not? Yeah, 0, 2, 9, 29. So it's not set to 29 microliters. 29 is well below the 200, so it better not be set to 29 microliters. The way that you read a P1000 is you read it top to bottom, and then you multiply that number by 10. So this pipette, if it had a tip on it and you stuck it into liquid and you lifted your thumb up, you would actually be aliquoting 290 microliters. Okay. Now this might be hard to see because of the glare. If I do it like this, okay. But underneath the 9, between the 8 and the 9, I think maybe you can see tiny little black sticks. Okay. And each of these black sticks, I call it a tick mark or a hash mark, whatever. So it kind of looks like this. And then the pipette, there's an arrow that's part of the pipette that is going to point at one of those tick marks. If it is directly underneath the number 9, then you know that the pipette is set exactly to 290 microliters. Okay, so not shown on here, but I'll write it so we can see or imagine where it might be. The 8, the number 8 is over here, and the number 0 and 3 are on that side. So I'm gonna go ahead and turn this so you can see. Okay, so right now I'm turning it, and I am approaching the number 8. So one more time, now I'm approaching the number 9. Now I'm approaching the number 8. If I went the other direction, I'm going to start approaching the number 0 because I'm moving to 3, 0. And so that's what it looks like. So what it means is that each of these tick marks allows you to precisely set the pipette by increments of 2 microliters. So if you moved 1 tick mark over, really that would be 288 microliters. If you went this direction and had your tick and you moved it so that this tick mark is right over the arrow, really this is 292. So each of those tick marks is 2 microliters, 292, 294, 296, 298, etc. Okay, and if you needed to set it to 293 microliters, you would set this purple little arrow in between 2 tick marks, right? Because that first little black tick right here, if we zoom in, this first one is 292. And this second one is 294. So if you need 293, you set it somewhere in between those 2 marks. Okay. So the next common pipette in decreasing in size is going to be your P200, which that's the one I don't have with me here. I don't, okay? But this one's pretty straightforward. Again, it has a window for 3 digits. Again, you read it from top to bottom. And the P200 measures liquids from 20 microliters to 200 microliters. Okay, so it should never go below 20, and it should never go above 200. And so the P200, none of the numbers are red, they're all black. So let's pretend it was set to the same exact thing. The way that you can tell the difference between a P1000 and a P200, besides looking at what's on the top of the pipette, is are there any red numbers? If the answer is yes, and it's the top number, then it's the P1000. If all the numbers are black, you know it's a P200. Okay. And this uses different tips than a P200. And so the way that you read this, you read it top to bottom. What does it read? It reads 29. You don't times it by, if you want to times it by something, times it by 1. Times it by 1. But basically this is set to 29 microliters. This one also has tick marks as well. And this tick mark allows the pipette to be precise to the 0.2 microliters. So you can set it for 29.8. You can set it for 29.3. You can set it for those things and be pretty precise with it. Okay. So I see there's a question. I'll get to it in just a second. So you have a P20. I do have that here. Most times students get confused with a P20 and a P200, and that is because they use the same tips and they look very, very similar. I wish I had it to show you. Hey, that's it. Inside. Sorry, her whiny's driving me nuts. Okay, no more. I have a mouse outside. No, bed. Okay, so for a P20, this pipette can measure as little as 2 microliters and as great as 20 microliters. That's the range of the P20. And the P20, where are you? Here it is. This has a red number. So there's a couple different ways that you really can tell the difference between pipettes. And the red number here is on the bottom and it goes from 0 to 9, okay? And for me, the way that I memorized this when I started working in biotech is I was like, how do I read this again? Well, I divide by, no, that's too confusing. So for me, I'm gonna show you, the red is, you can't really see it on this pipette. It almost looks gray, but it's red. Maybe if I move it closer here, you can see that the top 2 numbers are black. The bottom number is definitely a different color. This bottom number is red. So for me, what I envision, so let's do some different numbers over here. Let's just go with like, I envision an imaginary decimal place between the top numbers and the bottom red number. And that's how I read it. And I have trained my eyeballs to do that. There's actually no decimal place here, but that's how I read it. So if, I'll set it here. I'll just do like, okay. So if I showed you this, I've done this for so many years. I don't read 137 anymore. I read 13.7. Okay, so if this right here was set to 137, I know that this pipette is going to actually measure liquids that are 13.7 microliters. Okay. And this tick mark, this one also has little tick marks. This can allow you to be as precise as 0.02. So if I moved this over one tiny little tick mark, I could do 13.72 or 13.68, depending on which way I move the pipette. Okay. Last but not least, typically a lab will use a P2 or a P10. They kind of are similar to one another. A P2, which is not what I have here, a P2 measures from 0.2 microliters. That is literally so small. Sometimes I'm like, did I add anything? I couldn't see. You just have to trust that your pipette works. So 0.2 to 2 microliters. And the P10 is 1 microliter to 10 microliters. So obviously I like this one for when you need really, really small volumes. And so this, I'll use the P10 because that's the one we actually have here. This also has a red bottom number, okay? And I also pretend there is an imaginary decimal point there. So right now this one is set to 4. And the 1 is here and the 2 is here, and these tick marks look like this. And then we have the arrow right here of the pipette. Okay. So the top number of a P10 can only be 0 or 1. It should not go more than that. And so this one that right now that I'm holding actually is set to 0. Because if it was set to 1, this would be outside the range and I'd be ruining this pipette. So right now this pipette, and I'll show you, is set to 0, 4, and then the little arrow thing, I'll even try to zoom in a little bit. The little arrow thing is right between the 1 and the 2. Okay. So I know that this pipette is actually set to 4.1, and then I count the tick marks. So it's on the second tick mark, so I know it's 1.12, 0.14. So this tick mark is also worth 0.02 microliters. I just want to try to draw some lines so that we can kind of organize this a little bit. There. Okay, great. So that's essentially all I'm going to show you with pipettes. So for you as a student, you need to be able to tell me by reading, you need to be able to read a pipette window cartoon. Like if I showed you a cartoon of a pipette set to a certain amount, you need to be able to tell me what that pipette is set to. And the clues that you can do that with is, does it have a red number? If so, is it the first red number? Is it the third red number? You should also be able to tell me how many microliters each pipette will pipette in terms of range. So what I'm talking about is these things here. Like if I asked you, okay, the protocol says to aliquot 336 microliters. What would the window look like and what pipette would you use? You should be able to do both of those things. Okay, so at this point, I'll go ahead and take a question. So I think Kylie, do you still have a question?
Yes, just for clarification, so there would be 4 tick marks between each number. Like let's say it's P1000 and there'd be 4 between the 9 and the 8.
Yeah,
right?
It would look like,
Okay.
let's say this is 9, this is 8. You would have, that would be 280, 82, 84, 86, 88, 290. So this tick mark would be directly under the number 9. This tick mark would be directly under the number 8. And then yes, you'd have 4 tick marks in between. So this would be 0.2, 0.4, 0.6, or 2, 4, 6, 8, whatever pipette you're in. Yeah. Okay, any other questions? Cool. All right, last but not least, serial dilutions. And I'm not going to go into great depth with this, but I'm going to just kind of describe what a dilution is and how that's different than concentration. And then I'm going to provide you with just a background on how you would do a dilution. So the key comes really from the name of this whole entire procedure. So serial means doing something the same way every single time and doing it multiple times in a row. That's what serial means. Serial diluting, serial killing. Okay. Dilutions are just taking something that's really concentrated. Maybe you know the concentration, maybe you don't, but diluting something means basically just adding water to make it less sweet, less sour, less flavorful, less concentrated. Okay, you're just diluting it with some kind of diluent, typically water or some other similar buffer. Okay, so diluent, you're using a liquid as the diluent. Okay. Now, you can dilute something by half, right? So you can say like, ooh, this is 2 times too sweet. So I'm gonna add the same amount of volume and now I'm gonna cut the concentration in half. You can dilute, that's called a factor of 2. If you dilute it in half, 1/2, you're dividing the concentration by 2. That dilution factor is 2. Okay? This dilution factor is called DF. DF stands for dilution factor. If you had a dilution factor of 10, like this example on the slide, that means anytime you do this dilution, you are hoping to cut the concentration by 10. You're hoping to divide the concentration by 10. You want to make it 10 times less concentrated. All those phrases are synonymous and equal one another. Okay, so this value right here, this tells you the factor by which you're going to dilute the original solution in, or one of the solutions. Okay, so when you're writing, so if you had, let's go here, I'm just going to use this slide really quickly. If you had something that was super duper concentrated, so let's make it so navy blue that you can't even see through it. Something so concentrated. This is a very high concentration of blue molecules. There's a lot of those molecules in there. And if you wanted to make a dilution at 10-fold, which means a factor of 10, which means DF equals 10. So if DF was 10, you're essentially going to decrease those number of blue molecules by a factor of 10. If this one had, I don't know, 1,000 molecules per mil, then the next one, if you decrease it by a factor of 10, the next one would have 100 molecules per mil. Okay, so just a really rough cartoon. That means this one still have molecules in there, but you have diluted it by a factor of 10. And if you did your pipetting right, oops, molecules divided by mils. Okay. If you did the dilution again, okay, remember it's serial, so you're not going to change the DF. You're going to do the same exact thing again. And you had a DF of 10 again, and it's the same volume again. Now you would have approximately 10 molecules per mil. Okay. And if you did it again, serial dilution, same volume, but you've diluted this solution. You've diluted it by a factor of 10. You've basically cut the concentration by 10. So if you cut this concentration by 10, 10 divided by 10 is 1. So this, in theory, would have 1 molecule per milliliter. Okay. And that's what a serial dilution is. So how do you do the math for this? So a couple things I want to mention is that common DFs are factors of 2, factors of 5, 10, and 100. But in theory, you can do a DF for you can do any DF. You can do DF of 3, 4, 7, 22, whatever you want, because you just need to know how to do the math. Okay. So when you're solving for serial dilutions, let's do a different serial dilution than the slide suggests so that you then have an extra problem you can try on your own. So let's do a DF of 2. Okay. And let's say we want to do serial dilutions and we want to make 4 dilutions total. So you have your stock plus 4 dilutions that you're going to make. So this is your stock. In this example, this was your stock. Your stock is always called 1-to-1. And then if you divided the concentrate, if you had a DF of 10, this next tube would be called 1-to-10. And then if you did the dilution again, this next one would be called 1-to-100. Each time you're just multiplying by the dilution factor. And this is 1-to-1000, etc. Okay. So right off the bat, you know what the tube should be labeled for a DF of 2. So you'd have your stock, which would be 1 to 1. Your first dilution would be 1 to 2. Your next dilution would be 1 to 4. Then 1 to 8, and then 1 to 16. Okay. If you happen to know the concentration, so dilution is not concentration. Dilution, there's no values, there's no grams over volume, there's no mass over volume. So this would be your dilutions. And then that is different than your concentration. If you happen to know the concentration of your stock, let's say the concentration of the stock was 800 molar. Okay. Every time you're cutting the concentration by half, you're just dividing by 2. The same way we kept dividing by 10, you just divide by 2. So that means the 1 to 2 dilution in theory would be 400 molar. The 1 to 4 dilution in theory would be 200 molar. The 1 to 8 would be 100 molar. And the 1 to 16 would be 50 molar. And you can keep doing this for 100 tubes if you wanted, it doesn't matter. Okay? So this already sets you up with some sort of relationship between dilution and concentration. The more diluted something is, the less concentrated it becomes. Okay. So finally, we're going to make 4 dilutions. The last piece of information that we need to know in order to do this would be the volume. We need to make a certain volume. How much volume do we make? Let's say for this example, we are going to make 5 milliliters. Okay. So you need to figure out 2 things. And I suggest, remember, we're doing math on paper, but we're doing this all because we want to write instructions for someone that's going to make this in the lab. So all the math has to be done first. So the first, let me sit down. Okay, so the first piece of math that you need to do is solve for the amount of previous solution you need. So the volume, and I'm going to put it in quotations right now, previous solution needed. Okay. So when we're making the first dilution, when we're making the 1 to 2, the previous solution is going to be the stock. When we're making the 1 to 4 dilution, the previous solution is going to be the 1 to 2. When we're making the 1 to 8 solution, the previous solution is going to be the 1 to 4. So that's what previous solution means. Okay, so to figure out the amount of previous solution, all you got to do is super simple. What's your total volume desired? Divide by your dilution factor, and this gives you the volume of the previous solution you need. Okay. So in this example here, the total volume we said was 5. So 5 mils divided by the DF. We said the DF was 2. So the volume needed of the previous solution is 2.5 mils. Okay, cool. We're not doing anything in the lab yet. We're doing all our math first. The second math we need to figure out is the volume. Remember, we're diluting stuff, so we have to dilute it in something. That something is called the diluent. In this case, we're calling it water. What is the volume of the diluent that you need? So that's also really easy. You just take the volume that you desire, the total volume, then you subtract the volume of the previous solution, and this gives you the volume of the diluent. So in this example, total volume desired is 5. Volume of the previous solution, we literally just solved it, 2.5. That means the volume of the diluent we need is 2.5 mils, okay? Anytime you're doing the DF of 2, those two values are going to be the same, but it's not the case for DF of any other number besides 2. Okay, so I'm going to go ahead and delete this little cartoon that I drew here. So we have space. Delete. Okay, so let's go ahead and make this new DF of 2. There's your stock. This happens to be red molecules, the 1-to-1 stock. So now when you're in the lab, this is what you're going to do. You're going to set up all your tubes first. So how many extra tubes do we need? We need 1, 2, 3, 4. So let's see where I'm going to write this. Here. Set up appropriate number of tubes. Okay, so let's do that in cartoon form. So we have tube 1, tube 2, tube 3, tube 4. Okay, then we label them. You don't add anything into anything until it has labels. So you're going to take a Sharpie and you're literally going to write directly on the glass tubes. You don't even need lab tape. And you write the dilutions at the top that you were going to make. Okay, they're labeled. Awesome. Now what you do is you're going to add the diluent to all of your tubes because the diluent never changes. The volume of the diluent never changes. So if you need to add 2.5 mils to all those tubes, then add them all at once. It's a lot more time efficient to add diluent to all these tubes rather than add it to here, make this, mix it up, change the tip, do it again. So science is all about saving time. So you want to add diluent to all tubes. Okay, so in this case, we're going to add our 2.5 mils of water to each of our tubes. Okay. You can use this pipette and you have to use it a couple times, right? Because this only goes to 1 milliliter, so you'll have to do this twice and then set it to 0.5. Or you use this other really cool pipette that I don't have here in the lab, which is what most people do. It's almost like a hybrid between a really, really skinny graduated cylinder, but you attach the graduated cylinder to the end of a pipette. So you're not pouring it, you're actually using pipette motion, but the tip is a long, skinny graduated cylinder. That's what you would use for 2.5 mils. So you add your diluent to all of your tubes, all of them. Once you do that, then here's what you do. You add the appropriate amount. So I'm not writing appropriate amount, but you know to. You're going to add the appropriate amount of volume of the previous solution. And you're going to transfer it to the next tube. And then what's the magic last step that you always have to do to get full credit? Mix. Okay, so if I had to draw this in cartoon form, you would take your pipette or your serological pipette, that's the one with the graduated cylinder at the bottom, and you would take out 2.5 milliliters and you would put it in here, 2.5 mils. Okay. And then you mix. You can put it on the vortex and make it brrr, or you can take the pipette and move your thumb up and down. That mixes the solution too. And so essentially what you have now is something that's half as concentrated. And then you 5. Repeat 3 and 4 until you reach 1 to 16. Okay. For this example, right? You keep repeating it until you have finished making this last dilution. So over here, keep going, keep going. And that's it. That's a serial dilution. And so with that, I think that you will have a good idea of how to do some of the questions on the worksheet. I'm going to leave this example here for you. So the example we did as a class was an example using a dilution factor of 2. This example here is a dilution factor of 10, and it kind of walks you through this. But you can even practice if you assume that the stock is 450 grams per mil. You could also tell me what the theoretical concentration of each of these things are. And then you didn't see this one, but you're going to do this one. Okay. One more practice one for you. 6 mils is your desired volume. DF of 2, let's change that. Let's change it to 5. So each dilution is going to be a 1 to 5, 1 to 25, etc. Okay. And then you want to make 4 dilutions. So the stock is going to be 1 to 1. And then you want to make 4 additional dilutions. And that's it. And so this essentially is what we're going to do next week. We're going to see how spectrophotometry and the absorbance of light molecules can come into play and help us understand concentration for things that we don't know the concentration to. And that will make more sense when you read the manual. Okay, any questions about the serial dilutions or even pipettes? Okay, great. So end of lab, last thing that I do for the end of lab is take us back to Canvas, look at the lab page one last time. So when everyone leaves lab today, you have a good impression of what needs to be done before the next time I see you again. So let's go there. Give me a second. Okay. All right, so modules, we're in week 1. Week 1, and a lab. Okay, so you will be assigned a worksheet. A worksheet is there for you, and it's also here for you. So we'll take a peek at what's on the worksheet in just a second, but the format is the same. As discussion, you type the questions in bold, you type your answers not in bold, you embed any work by hand that you have to embed or drawings that you have to make, you draw them out and you put them into your document. The reading that you need to do is so that you come prepared. You're going to be reading parts of the bootcamp manual that are on Canvas. So this manual has 3 sections and we are modifying it to fit an online format. So the only part of the micropipetting technique that you need to do is a background. It just provides a little more information about pipettes because it's important if you're going to take molecular biology that you leave at least with some knowledge of pipettes. If you can't use them with your hands, you need to know about them. And then determining the concentration of samples using serial dilutions and spectrophotometry. So you're going to read all of that because we're going to actually do that activity. And then you're going to you're going to create a formal figure that would show up in a research article, and you are going to describe the conclusions from it. Me, of course, will collect, I will make the data for you, record it, and you will actually analyze and interpret that data. And then the other 2 things that you need to read are how to read scientific research papers, because you will be doing a lot of that in this class. So these are kind of how-tos for beginners. I think one of them is said for the non-scientist. It should be really labeled for the beginner scientist. And let's see. This right here is kind of like my cheat sheet for reading scientific articles, and this is kind of what I still have in the back of my mind. This is how someone taught me how to read scientific papers. No, it wasn't Dr. Raff, but it turns out that the person that taught her how to read research papers, come to find out after I was like, wow, this is such a cool article. This is exactly how I read it. Wow, it's so similar to how I was taught. Well, it turns out that the professor that originally taught her how to read research articles is the same professor that taught me. So I really learned how to efficiently do it at UC Santa Cruz as a grad student. And so you're in a really good position because you're now learning it as an undergrad, which is way further than I was. I struggled and I wished I knew how to read them better when I got to grad school. And she learned it from the same professor when he used to work at Indiana University. So I thought that was really cool because I found this without knowing that we had the same instructor, and then she gave him props at the end of the article. His name is Dr. Bill Saxton. So he just recently retired from UC Santa Cruz. So the worksheet, if we just take a quick peek at it, you'll see that most of the worksheets, most of the activities have questions about what was covered today in lab. So stuff about micropipettes and conversions, okay? Some questions about lab calculations, okay? Some serial dilution stuff, some stuff that we worked on in class today. And then a couple questions about what's gonna happen next week in more of like an intellectual, like let's really think about it, okay? So everyone turns in their own. It's due Lab Eve next week, and you're welcome to collaborate. Go to that Discord link, go work with people. Just make sure that your work and that your answers are in your own words. Okay, so with that, I think we're gonna call it quits for the day.